Today, we will solve some problems on the topic of semiconductors, which we discussed. The first problem concerns the calculation of the distance between near neighbors. In germanium crystal, whose lattice parameter is given 5.62 angstroms. Germanium and silicon both have a cubic unit cell in which the structure is that of diamond, which is shown in the figure. With the atoms at the origin, which is at the vertex of a cube, at one vertex of the cube 0 0 0, and then at a distance of 1/4 1/4 1/4 along the body diagonal. Atoms are at these points. This is the basic in a unit. So, this is the unit cell which is shown in figure, and we have to simply use geometry, and the distance which is asked is just root of 3 by root 3 by 4, which is root of 3 by 16 times 5.62. That is the distance required between the atom at 0 0 0 and the atom at 1/4 1/4 1/4, and that works out to be 2.43 angstroms. Having done the geometrical calculation, the crystal structure calculation, we now pass on to the calculation of the intrinsic carrier density. In silicon. Which is another well known semiconductor. We are given that the intrinsic resistivity at 300 K is given as 3.16 into 10 to the power 3 ohm meter. So, we are also told that the electron mobility, well, I do not think we have discussed the concept of mobility so far. Let me introduce the definition of mobility is the velocity of electron per unit electric field. We all know that the current density is in general given as J is NeV, where N is the carrier concentration. And E is the electronic charge, V is the velocity. So, and we also know that this current density is related to the electric field via the conductivity. This is the electric field, and sigma is the conductivity, electrical as we all know, this is just Ohm's law. So, because of these we can write NeV is sigma E, and therefore, sigma is NeV by E, and it is this quantity which we have defined as the mobility. Therefore, sigma is Ne mu. This is a very basic relationship which gives the electrical conductivity in terms of the carrier concentration, the charge and the electron mobility. And in this problem, we are given that the electron mobility in silicon at 300 K is 0.14 meter square per volt second. The unit of mobility is velocity is meter per second and the electric field is volt per meter. Therefore, this is meter square per volt second. So, that is given as 0.14 meter square per volt second, and the mobility of holes is given as 0.05, 0.05. And the current density is due to the presence of both electrons and holes in the silicon. So, there is a contribution from the motion of electrons among states in the conduction band and also the motion of holes in states in the valence band. Both contribute to the current density, and since the hole is positively charged and moves in a direction opposite to that of the electron in the given electric field, therefore, the current densities due to both electrons and hole add up, and therefore, we have a general relation using this fundamental relation. Now, I can write Ne E mu E plus NH E mu H, where E is mod E, the sign of the charge is included in the directions. Therefore, this is just Ne mu E plus NH mu H times mod E, and that is the general expression for J, and therefore, sigma, and we also know that the resistivity rho is just 1 by sigma. Since it is a cubic material, we do not have to worry about anisotropy here. Sigma and rho are the same scalar quantities with just one value for the entire in all the directions inside the crystal. So, we are given the value of the resistivity, therefore, going back to this is equal to 1 by rho. Rho is given, and since it is intrinsic material, the number of electrons is equal to the number of holes. So, let us write it together as N, so that this becomes N E mu E plus mu H. So, we have this. So, and we are asked to determine n, the intrinsic carrier concentration. N which is asked, which is required, is just given by 1 by rho times mod E times mu E plus mu H. So, plugging in the values, the given values for the resistivity, the electronic charge is known as standard value, and the values of the mobilities are given. Substituting all this, we get the value the carrier concentration is 1.06 into 10 to the power 16 per meter cube. Next we pass on to a case of intrinsic germanium. We are given the intrinsic carrier concentration. In germanium at 300 K, and that is given as 1.7 into 10 to the power 19 per meter cube. We are also given the value of the density, bulk density of germanium as 5.32 into 10 to the power 3 kilograms per meter cube, and the atomic weight of germanium is given as 72.59. So, the number of germanium atoms per unit volume can be calculated using Avogadro number, the density and the atomic weight as 4.4 into 10 to the power 28. We are asked to assume that this germanium is doped with pentavalent impurity atoms at doped with, and the doping concentration is 1 part per million, which is 10 to the power minus 6. So, this is the number of germanium atoms and the number of impurities. These are donor impurities, they donate electrons. Number of donor impurities is, standard notation is ND, and that is taking this number 4.4 into 10 to the power 28 and 10 to the power minus 6. So, 10 to the power 22 per meter cube, and we assume that all of them are ionized, all the impurity atoms are ionized. So, the number of electrons donated, which are the majority carriers, is the same number. Each impurity atom donates an electron. So, that is what we call usually N with a subscript E. So, we were asked to calculate several quantities For example, the factor by which, by what factor the majority carriers exceed carrier concentration exceeds the intrinsic carrier concentration. So, all we have to do is, we are given the intrinsic carrier concentration and we have determined the number of the majority carrier concentration, namely that of electrons. So, we divide one by the other and get this factor as, the answer is 2588. There are 2588 majority carriers for each intrinsic carrier, and since we know the number of, this is what we know as Ni, intrinsic concentration, and therefore, the whole concentration, whole, which is the minority carrier, concentration is given by NH equals, is such that NH times NE is Ni square. So, we know NH is Ni square by Ne. So, substituting Ni and Ne, we get the value of NH as 6.6 into 10 to the power 15 per meter cube. Because we know the majority and minority carrier concentrations and we have been given the mobilities of the electrons and holes, we are now in a position to calculate the conductivity contributed by the electrons and holes, and hence the total conductivity. Sigma, which as we have seen, Ne mu E plus NH mu H times mod E. So, Ne is known, NH is known, and therefore, we can calculate the conductivity, and this turns out to be that is the value for the conductivity with the given mobility values. Next, we pass on to the case of gallium arsenide. As we have already seen, gallium arsenide is a compound semiconductor with gallium and arsenic, gallium from the group 3 and arsenic from group 5 in the periodic table. So, it is a 3 to 5, 3,5 compound, and we already saw in the lecture that it is a direct band gap semiconductor, which means that the bottom of the conduction band and the top of the valence band lie exactly one above the other. So, these two are just above each other, and this difference in energy is the energy gap whose value is given in the case of gallium arsenide as 1.4 electron volts. We are also told that this sample is irradiated with photons of energy 1.6 electron volt. So, the difference in energy 1.6 and 1.4 gives you the kinetic energy of carriers. That is the kinetic energy of the carriers, and since this is say E, and therefore, the momentum is just root 2 m E p. And for the momentum, of course, in this case the mass is involved. So, the momentum will be different for the electrons and holes, because the effective masses are different. So, the momentum of electron is root 2 m e star E. So, substituting the effective mass of the electron, which is given as 0.07 times that of the electron, free electron. Therefore, substituting that, we get the momentum as 6.385 into 10 to the power minus 26. Momentum kilogram meter per second. Proceeding in the same way, we get the momentum of holes to m h star E, where this is effective mass of the holes. So, that is again given to be 0.068 times that of the free electron. So, substituting this value, we get the momentum as 6.29 into 10 to the power minus 26 kilogram meter per second. In the next problem, we are given data in the tabular form for the resistance of germanium, electrical resistance of germanium is given as a function of temperature. So, we are given the values in ohms of the resistance at 312 K, 354 K, 385 K and 420 K, and we are asked to determine the energy gap at as a function of temperature. Resistance R. So, determine energy gap of germanium, that is the question. And for this, we know that the resistance has a temperature dependence, which has the form where E g is the energy gap and K b is the Boltzmann constant. Therefore, we take logarithms so a plot of log r or log also. Versus 1 by T is a straight line. Whose slope is Eg by 2 kb. So, plotting this graph of log r versus 1 by T from the given values, we get a straight line, and the slope gives the energy gap in terms of twice the Boltzmann constant, and so we can determine the energy gap. The energy gap turns out to be 0.6 electron volt from the given data. Next question concerns the comparison of the conductivity of silicon. Conductivity means always electrical conductivity in this case. Silicon is 3.16 into 10 to the power minus 4 at room temperature. And that of germanium is also given at room temperature as 2.12 ohm meter minus 4 orders higher. So, we are asked to what temperature. Obviously, if silicon is heated, the conductivity increases. If it has to have the same conductivity as germanium, to what temperature should silicon be heated? So, that is the question. So, we have sigma 300, we take this as 300 K is for sigma naught exponential minus E g by 2 kBT for both for silicon as well as germanium. So, we can write it separately for the two. Of course, the energy gap values are different. So, the energy gap in this case is 1.1 electron volt, and in this case this is 0.66 as we just now saw. So, we get using this eliminating sigma 0, we get T as 506 Kelvin. So, you have to heat silicon to 230 degrees Celsius for it to get the same conductivity as germanium at room temperature. Next, we are given the intrinsic carrier density of germanium as 1.7 at 27 Celsius, which is the same as 300 K, as 1.7 into 10 to the power 19 per meter cube. So, we are asked to calculate the resistivity. Of course, electrical resistivity. We are given electron and hole mobilities. For germanium, they are given at this temperature as 0.139 and 0.19 meter square per volt second. Therefore, with this we can write the usual conductivity formula. Where of course, Ne and Mn are the same, therefore, we need not even write this like this, where N is the common concentration. So, the resistivity is 1 by sigma. So, this is 1 by sigma, and therefore, we can calculate from these, substituting, finding sigma from here and then taking the reciprocal, we get the value as 0.462 ohm meter, which is the answer. We are then given a problem on silicon. Here it is the inverse problem, the resistivity is given. No, that was 3. Resistivity at 300 K. So, we are asked to calculate intrinsic carrier density. With the data on electron and hole mobility in silicon. So, this is given as 0.15 and 0.05 meter square per volt second. So, this is mu E, this is mu H. So, we have to calculate the intrinsic current density, which is straight away given by So, substituting all these values, we get 1.6 into 10 to the power 16. The last question concerns the Hall effect in a semiconductor with 2 types of carriers, electrons and holes. So, we discussed in the lecture the Hall effect for a semiconductor with 1 type of carriers. Now, Hall coefficient. So, that is what we are asked to determine. So, suppose we have an external field, Hall effect is an effect which is produced when there is an external field applied at right angles to the direction of motion of the carrier in a current carrying semiconductor. So, external field is taken along y. So, let us call it E y. So, the electron current density will be J E y, which will be carrier concentration, electron concentration times the electron charge times the speed of the electron along the y direction, and this in terms of the mobility, it is mu E, mobility of the electron, times the field E y. Similarly, for the whole current density, H y, that would be by the same token it will be N H E mu H E y, and therefore, the total current as we already discussed, the holes will move in a direction opposite to that of the electrons. They will move along the electric field direction, and these electrons will move opposite to the electric field direction, but since they are of opposite charges, the current densities will be added. So, this will be N E mu E plus N H mu H times E E y. Now, because of this current and because of the magnetic field is taken, it should be at right angles to the electric field y direction as well as the initial current density. So, we take it along the z direction. So, the force, the Lorentz force on the electrons, which will be in the direction perpendicular to y and z, namely x direction. So, we write it as F x e will be E v y e b z. Force acting on the hole is E v y h b z. So, the Hall field, because of the lateral movement of the electrons and holes, there will be Hall fields, which in the case of the electron it is directed along the x direction. Therefore, this is E v y E b z, and for electrons due to motion of electrons in the x direction, and for holes similarly it will be E x equals E v y h b z. Therefore, E x in these two cases will be minus v y e b z, which in terms of the mobility it is mu e times E y b z, and for this is for the electrons. And similarly, E x will be E v y h b z, which in terms of the mobility is mu h E y b z. This is for the holes. So, since there is a Hall field in the lateral direction given by the sum of these two, there will be a current density, a motion of carriers, and there will be a current density contributed from both, which is given by the standard relation N e mu e. Therefore, the Hall current densities due to electrons, electron motion, and that will be N e E mu e using this times that electric field. So, that will be minus mu e E y b z, and for the holes similarly for hole motion. This will be N h E mu h into mu h E y b z. So, the total current, the net Hall current will be E times NH, taking these two, NH mu H square minus NE mu E square times E y B z. So, this will be the Hall current density. So, this Hall current density will be result in a Hall field due to this current density, and that is E x is J x by sigma by Ohm's law again. Therefore, this will be E times, borrowing this expression, NH mu H square minus NE mu E square into E y B z by the conductivity, which is NH mu H plus NE mu E times E. So, and the Hall coefficient R is just E x by J y B z, and that will be, borrowing this expression, NH mu H square minus NE mu E square times E y B z by NH mu H plus NE mu E here times J y B z, and this is nothing but sigma E y B z. So, this will give me, simplifying, substituting for sigma again, that will be the Hall constant in a semiconductor containing two carriers. And it is a simple matter to go from here and show that this will lead to the standard expression R equal to 1 by N E in the case of a semiconductor with just one type of carriers.